Hi everyone. Today we'll take a look at exponential functions and logarithmic functions. So exponential functions will be a fairly small part because a lot of the things such as properties of exponents and all sorts of those things you've already learned before starting IB mathematics. So I'm just going to do a quick refresher, part of this for like the first 10 minutes. Then we're going to go into detail for logarithmic functions, looking at properties and solving a few questions. All right, so exponential functions, it's a pretty straightforward function, right? So it's, you can think of it like an exponential decay or an exponential growth, right? So essentially the general form, right? So the general form is like this, right? So it's y is equal to a times x, right? Where a is some constant, right? Some constant. It can be positive, negative, whatever, right? So the general graph, right? So the general graph comes something like this, right? You can all, you can put this in decimals. You can put y is equal to 2 raised to the power x, or 3 raised to the power x, anything but one, right? Because if you put one, you're gonna get 1 raised to the power x. 1 raised to the power anything is just one. So you're gonna get a straight, straight horizontal line. So if I draw, my axes like this, so my y and my x, this, right? So if I change the color, so I'm gonna get something like this. Maybe the general thing is always like this, right? It's gonna be much more smoother than this, obviously, because I'm just free drawing it. And this part is always gonna be 0, comma 1, right? Because any constant raised to the power 0 gives an output of 1, right? So let's look at a few details of this. So let's look at domain. Domain. So in this case, right? In this case, there is no restriction, right? We can take any value of x, from negative infinity to positive infinity. So, I can say x essentially belongs to all real numbers, right? What about range? What about range? So, when this is positive, right? When a is positive, right? We're always going to get values greater than 0. So, y is always going to be greater than 0, right? Or if you want to put in different terms, you can say basically it's going to be from 0, not touching 0, to infinity, like this, right? Obviously, if you add a negative sign, we're going to have an exponential decay. Okay, so when we have an exponential decay, sorry, that's going to be for negative x, my bad. If you have negative a raised to the power x, it's going to be something like this, right? So I can change the color. So let me write it in green maybe. So for y is equal to negative a to the power x, right? We're going to have something like this, right? It's just a reflection over the y-axis. Sorry, the x-axis, my bad, right? So it's going to be, proper reflection like this, right? We're going to have something like this, right? So in this case, the domain would remain all real numbers, but here the range would be from, 0 to minus infinity, right? So, or minus infinity to 0, right? So minus infinity to 0. That's the range, right? We can also have something, like, let me change the color again. So I can take yellow. Sorry, not yellow. This time I'll take orange, right? So maybe you can have y is equal to a raised to the power minus x. So in this case, what we're going to have is like this. Let me just do a quick axes really quickly. This, you're going to have an exponential decay. So it's going to be like this, something like this, of this sort. And here also, so this orange curve and this yellow curve, they're reflections with respect to the y-axis this time, right? That's what they are. So let me just erase this and draw it again. So this and like this, of this sort. So this is what this curve looks like. Okay, so again, you must know your exponent rules, right? I'm not going to revise over those things. Those are pretty basic. You have to learn them through middle school and all. So now let's get started with logarithmic functions. What I want to explain is I'm going to use what we did in exponent function to understand the logarithmic function, right? Suppose we have something like n, or we used to say y is equal to a raised to the power x for exponential function, right? Exponent, right? That's what we used to say, right? So now what I'm gonna try to show is that log is essentially the converse or the opposite of exponential. Okay, so let me change the color here, and I'm gonna take blue, right? So I'm gonna say that n, I'm gonna get I'm gonna do a raised to the power x, right? And I'm gonna get some n number, right? So now I want to find what x is, right? I want to write x is equal to something. So the way I'm going to do is I'm going to use the log function. So it goes log base a n like this. So now I hope you can see how I'm correlating this, right? The x is the right here, the exponent, right? Log is the function, base a is the base of the exponent, and then n is the value that we get. So you can see, right, that a log is essentially an exponent. A log is an exponent, right? That's exactly what it is. Okay? So for example, let's take an example. Let's take a very, very simple example. So we're going to have log base 2 right here. So I'll change the color again. Okay? So I'll change the color and I'll take magenta, right? So I'm going to say, example right here. And I'm going to say log base 2 8 is equal to what, right? So essentially, this is equal to some number, right? So 2 raised to the power some number is going to give me 8. Well, by observation, you know that it's equal to 3. So n is equal to 3, right? Your calculator can easily do this, right? Without any difficulty, your calculator can do this, right? So right, so this is essentially how the log function works. Now, if I want to generalize it, right, what I can say is what we're going to have, or f of x, right, will always be log base a to the power x, like this. That's what our function is always going to look like. Okay, how the curve is going to look like, the general, path of the curve, we're going to discuss in the future videos. But for now, I just, need you to understand how the log function is operating at its core, right? It's an exponent. A log is an exponent. That is how you should remember it. You shouldn't get confused by what the log is doing. It's just giving you the value of the exponent, right? Whenever we have x as the exponent, we're trying to determine the value of x, and the only way we can do that is by using the log function, right? It's basically undoing the exponent if you want to think it, if you want to think about it that way. Okay, so now that we have discussed, the function, the general function, the general form of the function, let's look at some, details about what the function is, right? So let's look at, let's try to understand what happens, right? Let's look at a few more examples. So here, now we know that, this is equal to a raised to the power x, right? So again, if I write this as n is equal to log base a x, right? So I can rewrite this as x is equal to a raised to the power n, right? Okay. So now let's understand some properties. Okay. So if we take a to be greater than 0, right? This is our assumption that we're gonna work with for now, because a can be less than 0 as well, right? A can also be less than 0. So I'm gonna take a is greater than 0 for now. Okay, like this. Okay, and a cannot equal 1, right? So let me just make another assumption here. A does not equal 1, because remember what I told you, 1 raised to the power anything gives you 1, right? So we're going to avoid that. Okay, and we're going to take one more assumption, that n is greater than 0. Okay, so let me erase this one more time and say n is greater than 0. Okay, so let's take another example now. I'm just gonna work with a lot of examples, so you get an idea of how you're able to relate the log function and the exponent function within them, between themselves, right? So let's look at an example, right? So we have log base 2 is equal to x, right? So if I want to rewrite this, I'm going to write base, log is an exponent, so the x is the exponent, so this is the base. So 2 raised to the power x is giving us 2. Now, it's pretty obvious, and if you want to get the same number again, you have x has to be 1, right? It's pretty simple, nothing too crazy. Right, let's change the color. I'll go with red. Okay, so let's look at another example here. So the example, it will be log base minus 2, right? This time I've changed it, okay? This is the general form that I did, but we can also have a base as negative, okay? So log base negative 2 is 2 gives us is equal to x, right? So we can rewrite this as negative 2 raised to the power x gives us 2, right? Like this. Now, obviously, by observation, you can clearly see that this is impossible, right? Negative 2 raised to the power anything, right? So it should be 1 here, right? But that's not possible. So this is not possible, okay? This isn't possible, right? This is never going to be possible, okay? So that's something, I want you to be aware of, okay? Now, okay, let's look at one more example, okay? So now we have example one more. So I'm going to take log base negative 2 again, 4, right, is equal to x. So I can say negative 2 raised to the power something is giving us x, right? So raised to the power x is giving us 4, not something, 4. Okay? So again, you can clearly see that x is equal to 2. Like, these are very simple questions that you can solve by observation. Again, if it's paper 2, you can use your calculator. It's no big deal, right? Very simple, right? However, again, the issue with this is a negative base is not possible, right? So negative base is not possible, or it's not allowed, okay? So that is important to be aware of, okay? Not allowed, okay? This is key, okay? So the base, or the a, must always be greater than 0. The base in this function, right? This function is set up such in a way that you can't have a negative base. So a must be greater than 0. This is very important. Although this was reversed, if you worked, in a reverse manner, it seemed possible, but it genuinely isn't possible at all. Okay? Only the first example works really well. Okay, so now let's look at a few example questions. All right, so we have the question log base 7 49, right? We're supposed to simplify this. Well, let's say is equal to x, right? So we know that a log is an exponent. So log base 7 49 is an exponent. So I can rewrite this as 7 raised to the power x gives us 49. Okay, so now, again, by observation, you can say that x is equal to 2, right? X is equal to 2. Okay, let's look at another question. We have log base 5 is, 1 by 5 is equal to x, right? Find x. So I'm going to reverse it every time. I'm going to reverse it. So I know 5 raised to the power x is equal to 1 by 5, like this, right? Now, again, by observation, I can see that x is equal to negative 1. For those who couldn't, let me know. I can rewrite this again. So I can write this as 5 raised to the power negative 1. Bases are the same. Just compare the exponents. So negative x is equal to negative 1. So x is equal to 1, right? Again, very simple, very straightforward. All right, third one is log base 6 square root of 6, right? We're supposed to simplify this. Again, I'm going to equate it to x every time, right? So I'm going to write base is 6. So I'm going to write 6 raised to the power x is giving me square root of 6. Now, square root of 6 is basically a power raised to the power half, right? So 6 raised to the power x is equal to 6 raised to the power half. So bases are the same. I'm just going to compare the exponents. X is equal to half, right? Let's look at number 4. So number 4 is log base 464. Okay, it's equal to x. Okay. Okay, I'm going to do 4 raised to the power x is equal to 64. Okay, so I know 4 times 1 is 4, 4 times 2 is, 4 times 4 is 16, 4 times 4 times 4 is 64. So this is actually 4 cubed is equal to 64, right? So x is equal to 3. Again, these questions are fairly simple, and you'll never get a question like this. I'm just trying to explain how you evaluate questions when you're given them, when you have log functions in them. Majority of the questions are going to require you to use the log properties with respect to functions and all sorts of things mixed together, right? This is just the basics. This is just the start. I just want you to get familiar with how you use the log, right? How you use the log function to solve these basic questions. And then we'll discuss the log properties as well. Okay, let's look at number 5 now. Number 5 is log base 10, 0.001, right? So I'm going to equate it to x. I'm going to write 10 raised to the power x is equal to 0.001. Right? Again, by observation, you can see that this is like saying 10 raised to the power x is equal to 1 upon 1,000, right? And this is like equal to 10 raised to the power minus 3. So x is equal to, sorry, not minus x, just x, right? Just x, okay? Like this, right? And I made a small mistake here as well. I just realized that because I was solving this question. So this is going to be x is equal to -1, right? So this is -3, and yeah. All right, so now I just want you to understand two types of log functions, right? That majority of the questions are going to deal with, okay? So I'm going to write two special logs, and you're going to deal with them majority of the time. Okay, so the first one is basically the log base 10, okay? Whenever you have log base 10 something, log base 10x, right? So you can always write this as log x. You don't need to write base 10 because whenever if you don't write the base 10, it is assumed that you're using a base 10, right? If you don't write anything here, it's assumed that you're using a base 10, okay? And suppose you're going to have log base e, right? I'm sure you have heard, the natural exponent e, right? It's around 2.7, right? So when you have log base e x, right, you're always going to write ln x like this, okay? Ln means natural logarithm. Okay, so you don't need to write base e every time. You're going to waste your time. You're going to waste more ink writing this, and so you just write ln x every time, right? When you write this, the examiner, your teachers, your friends, right, will understand that you've written the natural log. And believe me, 90% of the questions will require you to do this. When you do higher level calculus or whatever it is that you move forward with, 90% of the questions and topics or any examples that you study, they're all going to be with respect to the natural log of x. Okay, so this is very important, right? This is very, very important, right? This is very common, but this is highly important. You're going to see this more often than log base 10, right? So these are just the two questions that I want you to understand. Okay, so now let's look at a few more examples now that I've discussed these two logs. All right, so let's get the first example question. So I'm gonna have maybe something like this, right? So take number right here, example like this, right? I'm gonna have ln of e squared, okay? Ln e squared. So again, if you're slightly confused, no issues, I'll break it apart. So this is like saying ln, or I can say, sorry, not ln, log base e squared is equal to x, right? So I can write this as e raised to the power x is equal to e squared, okay? Bases are the same, just compare the exponents. So x is equal to 2. It's that simple, right? There's no rocket science here at all, right? Let me change the color. Let's take another example, right? Example right here. So we have log base 10, right? I'm just gonna write log, right? Log, just simple log means log base 10, right? So log, let's say maybe, I don't know, square root of 10, right, is equal to x, right? Obviously. So I know this is log base 10, so I can write 10 raised to the power x is equal to square root of 10, right? We all know that square root of 10, square root is basically raised to the power half. So x is equal to half, like this, right? So that's how it is. Okay, now that we've done a few questions, let's look at some properties of log functions. All right, so let's look at property 1. So property 1 is like this. Okay, it's as follows. Log base a 1 is equal to 0. For a does not equal to 1 and a is greater than 0. Okay, there's a reason why I've done this, right? If you take a is less than 0, right, you can plot it in Desmos, you're going to get a weird function, right? It's not going to be a log function. So let me just rewrite property. I don't really like the way it's written. So property 1, okay? Log base a1 is equal to 0. So let me just show you a small proof, right? So if I have log base a, right? A can be anything. It can be the natural exponent e, it can be 10, it can be a billion, it can be pi, whatever, right? So 1 is equal to x, right? So again, if I convert this to x, then I'm going to have a raised to the power x is equal to 1. Now, if you remember, anything raised to the power 0 is equal to 1. So x is equal to 0, and that's why we have a 0 for x, right? Simple property, nothing too crazy, right? Whenever you see something based something log based something 1, you can cut it out and replace it with a 0 every time, right? Let's look at the next property, right? So let's just scroll down right here, and I'm going to write property 2, okay? Property 2, like this, okay? So this one's going to be log base a is equal to 1, okay? So when the base and the final number are the same, the log or the exponent is 1. That's pretty much common sense, right? Let me just show you the proof really quickly though. So if I have log base a1, right? If I convert it to exponents, I'm going to have a raised to the power 1, right? A raised to the power 1 is equal to a, right? So this is going to be, anything raised to the power 1 gives its original number. So basically, x has to be 1, right? So if I'm going to write x here and x here, right? I'm going to have x, right? So this is 1. So x is equal to 1, right? Again, very common, very simple. If you see something like this, you can just cut it down and write 1 and replace it, right? Again, one more thing I forgot to mention, which I won't be doing again and again, but just know that a does not equal 1 and a cannot be negative, right? So yeah, right here. Cool. So let's look at property number 3. Now this is the interesting property. So property 3 says that basically if you have log base a n, right, plus log base a n, what we could do is if you want to add these two logs and the bases are the same, right? So we keep the bases the same. Inside we go m times n, okay? M times n, okay? So let me show you the proof for this. Okay, so if we have the two logs, right? So we have log base a m is equal to, let's say, x, right? X, very simple x. And we have log base a n is equal to y, right? So I can rewrite this as a raised to the power x gives us m, and a raised to the power y gives us n, okay? So we have these two now. Okay, so now if I want to, if I multiply both of these sides, both of these equations, equation 1 and equation 2, right? So what I'm going to have is a raised to the power x times a raised to the power y is equal to mn. Sorry, not my, mn, right? Like this. So now I'm going to have ax plus y is equal to mn, right? So now if I use the log function, I'm going to have log base a m times n is equal to x plus y, right? And remember what our x plus y was. Log x plus y was the sum of these two logs, which I've written right here. So like, this is x, this is y, and it's just log a m times n, right? It's a very simple property. It's a very handy property, okay? Right? So if I want to generalize this statement, I can even generalize this, right? So I'm going to do it right here. So I can basically say that, log base a log base a, x1 plus log base a x2 plus all the way down to, log base a xnth, right? Xn is basically equal to saying log base a x1 times x2 all the way till xn, right? So I'm just it can be used for multiple things. So it's not for two. It can be used for, n number of things because it's addition, right? Very simple, very handy property. You should, have this memorized as soon as possible. Okay, we're going to take a look at questions that require you to apply this property as well. So it's not like you're just, memorizing it for the sake of it. You have to memorize it, or you will memorize it as you move forward and do loads and loads of questions. Property 4. Okay, so I'm going to write log base a m minus log base a n is equal to log base a m divided by n. Okay, again, let me do the proof for it, right? So I'm going to do let x be log base a m, let y be log base a n. Okay, so I can rewrite this as a raised to the power x is equal to m, and a raised to the power y is equal to n, right? So now if I divide both of these equations, right? If I do equation 1 divided by equation 2, what I'm going to get is a raised to the power x times a raised to the power y is equal to m upon n, right? I want to simplify this. I can write this as a raised to the power x minus y is equal to m divided by n, like this. If I take the log on both sides, I'm going to get log base a m divided by n is equal to x minus y. Again, comes to the original property that I just stated, right? Very simple. Again, very simple. It's the same thing, right? It's not some rocket science thing, right? Let's look at property number 5. Okay, so just scroll down right here, take a new color. So I'll take lime, right? So property 5, right? Property 5. Right. So I'm gonna have log base a, right, m raised to the power alpha. Okay, so it's like this. It's like inside it's m raised to the power alpha. So this can also be rewritten as alpha times log base a m, like this. Okay, it can be written like this. So let me just take out this, just not to make it less messy. Okay, again, let me show you a proof. So let's take some constant k, right? So some constant k is equal to log base a m raised to the power alpha. Okay, so if I simplify this, I can write this as base is a raised to the power k gives us m times alpha. Okay, gives us m times alpha. So m is basically a raised to the power k upon alpha, like this, right? We can write this like in this form also, right? This is also appropriate, right? There's nothing wrong with writing what we have right now, right? So m is equal to all of this. Now I can write this as log base a k upon alpha is equal to m, because sorry, I'm really sorry. Log base a m is equal to k upon alpha, right? Because the log is an exponent, right? Like this. Okay, let me just simplify this right here, and I'll just clean up this part again. So, right, m log base a, like this. So k upon alpha, right? Now, if I multiply with alpha on both sides, I'm going to get k is equal to alpha times log base a m, like this. Okay, so I've proved this property as well, right? So proof, right? Proof. Okay, let's look at property number 6. Okay, property number 6 is kind of a very handy property as well, especially when you have to add two log functions with different bases, but they have something in common between them, right? It's kind of, I've phrased it very ambiguously, but you'll see when we do examples. Okay, so property 6. Okay, property 6 is like this. Log base, okay, so log base a, except in our base a is raised to the power some beta. okay, some variable beta, okay, and values m. So this can be simplified as 1 upon beta times log base a m. Okay, that's what it is. Like this. Okay, so let me just prove it to you really quickly. So let me show you the proof. Okay, so again, I'm going to take some k constant is equal to log base a, and the base itself is raised beta, right? We write a again properly. So a and m, like this, right? So now I'm going to write a raised to power b raised to power k, because remember, k is the exponent, right? Is equal to m, like this, right? So I can write this as m is equal to a raised to the power beta times k. Okay, so these two are being multiplied. If you remember exponent rules, right? That's why I said you need to revise them. Okay, moving forward. So now we have log base a, okay, m is equal to beta k, right? Right? Simple. We just, we had a log, we get a log into an exponent, and then we got it back to a log, right? So now if I divide by b on both sides, what I'm going to get is 1 upon b times log base a m is equal to k, right? Which is what I just showed you right here. Okay, so this is how this property is used. When you have something like this, you can take the beta outside, you can take that constant outside and write it 1 upon beta. Okay, now let's look at property number 7. Okay, property number 7. So change the color again. I'll take pink. Okay, so property 7. These are all important properties, so you're going to see them, and you're going to be required to use them sometime or another. Okay, so we have what it says: log base a, right? Oh, sorry, let me write it further up. Log base a m can be written as log base b m upon log base b a. Okay, so what I've done here, okay, just notice this very carefully. I'm going to take the pointer. So change the bases, right? So bases, there's common at the base is common, some b, some variable b, some constant b, okay? Now, they've broken apart. This is m and this is a. Okay, so this was the base previously. Now it's no more the base. Now the base is b, it's a common base, right? M remains where it is. Now a comes right here as the final value, right? So this is also a useful property, especially when you have especially when you have to break things apart. Again, I'm explaining it very ambiguously. You're only going to experience it once you start doing questions. When you see you need to use these properties, just know how it is, right? Let me show you the proof really quickly as well. So let me write proof, right? Proof. So we have some k is equal to log base a m, right? Like this. So m is equal to a raised to the power k, because remember, k is the exponent, log is the exponent, right? So now if I take another, or you know what, before doing that, let me just draw a separate line instead. And what I'll do is I'll look at this. Log base b is equal to m, okay? So log base b m, right, is equal to log base b a raised to the power k. Okay, I've just taken this assumption that it's raised to the power k. Okay, so if you remember the previous property that we just learned, right, I can bring this k out. Okay, so what I'm going to do is log base b m is equal to, right, is equal to k times log base b a, like this. Okay, right? So now if I divide, by this log on both sides, what I'm going to get is k is equal to, right? K is equal to log base b m upon log base b a. Okay, kind of a weird thing to wrap your mind around, but just know this property, right? Just memorize this property. That's the best way I can say it. It's very useful. Again, Just have to know that when I'm going to break this apart, the base has to be common, right? This value m remains as it is. The base a, takes a position similar to m right here. Again, maybe even if you have two logs like this upon each other, and you can go from this right hand side to the left hand side also. That it might also work that way as well. So just be aware of the different possibilities that can happen. Again, we're going to do questions, so don't worry too much about it. Okay, let's look at property number 8. So let me scroll down right here. Okay, so property number 8, I'll take beige. Okay, so no, I'll take light blue. So right here. So property 8. Okay, so property 8 says that log base a m can also be written as 1 upon or the reciprocal of log base m a. Okay, I've just reversed them. Okay, and I'm not going to explain the proof of this. Okay, use the property number 7 to prove property number 8. Okay, that's what I'm going to say. So for proof, what I'm going to do is use property 7. Okay, use property 7. Use property 7. Okay, I'm not gonna spend time proving it because it can get a little bit complicated, and just know the property. That's the key point here, not the proof, right? You're never gonna be asked to prove how this property works, right? They're not gonna ask you this. Okay, so now this is a very important property. So just property number 9. Okay, so property number 9. Change the color. So property. Second. Okay, so property 9. Okay, so property 9 says that a raised to the power log base a x is equal to x. Okay, that's what it means. So maybe if I have 2 raised to the power log base 2 to the power log base 2 4, this is actually equal to 4, right? This is what this property says. So a raised to the power log base a. Okay, these a bases must be the same in both places. Okay, if I have to prove this, let me try proving it as well. So proof will go something like this. Let's say we have some constant, right, is equal to log base a x. Okay, right? So x is equal to a raised to the power k, right? Now I know k is equal to log base a equal to x. I'm just gonna plug this in right here again. So x is equal to a raised to the power log base ax. Okay, that's all it is. That's all that there is to it. Again, like these properties, but by themselves don't really have a lot of value, right? But when you see them in questions, then you're actually going to be able to say, okay, this is what's happening to them. Right. So final property number 10. Right. So I'll change the color one more time to peach. So I'll say property 10. Okay. Let me rewrite 10. So have property 10. I'm going to have a raised to the power log base c is equal to c raised to the power log base b a. Okay, that's what it is. So if again, I'm not going to show you the proof of this one. It can get a little hairy as well. So just know this. Okay, just be aware of this. So what is happening is we have a base a, log base b is equal to c. So if I want to rewrite this, maybe what happens is log base bc can't be simplified, but log base b a can be simplified, right? That is why we change the order of this. So what happens is the c comes down as the base, right? This b remains as it is. It's just that a and c are just being swapped. So a comes where c is, c comes where a is, right? That can be done, right? Just be aware of it. That is possible, right? Maybe let's take a look at maybe an example. So log base, uh, let's say 3 is and then 9, right, or something like this. Or I know I'm going to take 4, and I'm going to take 16 here. So 4 16. So this is 2, right? Log base 416 is 2. So 2 squared is equal. So this would be 2 squared. This would give us 4. Now using the property, I would swap 16 and 2, right? So 16 and 2. So I'd have 16 log base 4 is 2. So log base 4, 2 gives us half. So this would be, 16 raised to the power half, square root of 16, which is basically the square root of 16, which is also 4. Right, so you can see how this property holds. Now, let's take a look at a few example questions. All right, so let's look at the first example question after learning the properties. All right, so we have example, right? So we have example. The first one says log 6 plus log x. Okay, that's the first example question. So again, because there's no base, we assume that there's a base 10 to it, right? Remember that what I previously said, these are common types. So now we have two logs being added together. So this can be seen as just saying log base 6x, right? We just multiply them. This is the property that we had. Log base am plus log base an is equal to log base am times n. So that's what it is. Log base 6x. All right. Now let's look at another question. Log base 5 plus log base, 2 times log base 3. Okay. So now what in this question we see that there's 2 times this. So remember, this 2 can become here as an exponent. So this, what will happen here is that I'm going to have log base 5 plus log base 3 squared. So this is 3 squared can be written as 9. Okay, so 9. Now again, it's very similar to the first question. So I'm going to have log base 45, right? Very simple, right? So I'm going to write an example here again, right? Let's look at another example question. So now I'm going to have, let's say I'm going to take log base B12, right, minus half times log base B9. Okay, so first thing I'm going to do is I'm going to evaluate this part. So I'm going to take this right here as an exponent. So 9 raised to the power half, right? So log base B12 minus log base B3. Okay, so 9 raised to the power half, or also known as square root of 9, is equal to 3. Now I can simply divide this, right? So this would be log base B4, right? So 12 divided by 3, 4. Okay, very, very simple. Okay, let's look at one final example question. Let me just scroll down, get some more space. So example is like this, okay? So it is log base 3m, right, plus log base 3n minus 2 log base 3p. Okay, I'm going to evaluate this. So if I evaluate this, what I'm going to get is log base 3m plus log base 3n minus log base 3p squared. Okay, now I can simplify and say this log base 3 is equal to m, right, m n upon p squared, like this. Right, that's what it simplifies down to. So that is how I use my log properties to solve questions. All right, so this is kind of an out of the box question. So we have to find the value of log base, whatever we have right here, right? So how can we start this question, right? That is the tricky part here. Okay, so what I'm going to do is I'm going to multiply and divide by this number right here, because I can see that these are like conjugates, right? The only difference is the signs in them, they're opposite, right? One's positive, one is negative. Right, so what I'm going to do is I'm going to multiply 2 plus root 3. I'm going to multiply and divide by the base, right? So what I'm going to do is, I'm going to do, just a second, sorry. So I'm going to do log base 2 minus root 3, okay? 2 minus root 3, the 2 plus root 3, right? I'm going to do 2 minus root 3 upon 2 minus root 3. Okay, that's what I'm going to do. So it's like this. This is like this. This is like this. All right. So if I multiply this, I'm going to get 4 minus 3, right? So it's a plus b times a minus b, right? Just a squared minus b squared. So I'm going to get 1 on the top, and I'm going to get 2 minus root 3 on the denominator. So it's going to be log base 2 minus root 3, like this. Okay, great. So now I can simplify this, and I can say that this is basically log base 2 minus root 3, right? Then I can say 2 minus root 3 raised to the power negative 1. Now, if you remember the property, if there's an exponent on this part right here, I can just take it out here. So what I can write it as log base, sorry, minus 1 times log base 2 minus root 3, right? 2 minus root 3, and then I have 2 minus root 3 here as well. So now this is like log base a, which is basically equal to 1. So 1 times negative 1 gives me negative 1, right? This is my final answer. All right, so this is also an out-of-the-box question. We have to find the value of this log, right? Log function right here. Okay, so one common thing I can see is that I can get a base 3 here and a base 3 here, right? So what I'm going to do is I'm going to write this as log base 3 raised to the power minus 1, right? And then here I'm going to write 3 raised to the power 3 by 2. Okay, that's something I can see. So I'm going to always try getting common bases. That's always going to simplify things together really well. So I can see that I can put this 3 by 2 outside right here. Okay, so that's exactly what I'm going to do. So I'm going to write 3 by 2, right? 3 by 2 times log base 3 raised to the power negative 1, right? 3, like this. And the other property which you remember is that if you have an exponent raised here, this part goes in the denominator. So this part simplifies. It's like 3 by 2 times 1 upon negative 1 that was here, right? Times log base 3, 3. So this log base 3, 3 is just 1. So our final answer is negative 3 by 2, right? You can use secant. I've again a direct use of the property. You can expect questions like this, but instead of finding exact values, you can see you can take, for example, you're gonna have some x and y and bunch of different variables. You have to simplify that together, something like that. But these properties are how you're gonna get there, right? Without using these properties, there's no way you can simplify this down any further, right? Let's look at one last example question, which is also going to be slightly out of the box, but it's going to use the properties that we have learned before. All right, so in this question, we have to find the value of x in this equation, right? So I can see log base 5 times a. This is some constant value. This isn't a constant value because we have x right here, right? Because of this x, it's not a constant value, but this is a constant, right? Some constant. Erase this and this, right? So what I can see is that there's an a here and an x here. So what I'm going to do is I'm going to break this apart, right? I'm going to use one of the properties, one of the ladder properties. So I'm going to write log base 5a times, I'm going to break this apart. I'm going to write log base 5x upon log base 5a. Remember that property where when I'd broken things apart, keeping the same base, right? I could have kept this as log base 6 and 6 as well, but I kept 5 because I want to get rid of this constant value here. I could have kept any value for this 5 that I'm putting here right now. I could have put pi, I could have put 10, I could have put 25, I could have put 99. It wouldn't matter, right? So now, and then I can write is equal to 2, right? So now this and this cancel. So I'm going to be left with log base 5x is equal to 2. 5 squared is equal to x, and x is equal to 25, right? So this was the final question. And again, it was a direct use of our property that we learned, right? It was nothing out of the box. We just need to be aware of the properties, right? And the only way you can do this is by, the only way you can get better at this is by doing loads and loads of questions from your textbook and from your IB past papers, right? Obviously, I can't, touch upon every single thing. We will take a look at more questions in the next video, right? Where I explain, where I solve more questions involving the log function, and maybe we'll touch upon how to graph the log function. If we don't touch upon it, the next video, maybe on the third video on log functions, we'll do separate. I'll explain how you plot log functions with different cases. All right. So again, just revise these 10 properties that I explained today. Two questions from the textbook, whether it's Pearson, Oxford, Cambridge, whatever. Um, Try and solve as many questions as you can to get yourself familiar, and so that these properties become second nature to you, right? The only way you're going to get better at using these properties is if you do questions, you're like, oh wait, in this previous question I had used this, so let me try using the same property number 7 or property number 8 again. Let me see if it works in this question, right? And I know you might say, oh, it doesn't work in this, but had the case been slightly different, it would have worked. Just keep thinking about where and when each property is applicable, right? That is the only way you'll get used to it. I know it's a lot. I've explained a lot in this video, but believe me, as you do more questions, you will be a lot more comfortable with it. All right, so this was all for today's video, and I'll see you in the next one. Bye bye.